Okay, Lambert's law and Bayes' law. The basic theory involved in colorimetry is concerned with the determination of concentration of light absorbing substance by the measurement of relative absorption of light with respect to a known concentration of the same substance. To detect the light absorption, we have to pass a known wavelength of energy. So how we will choose the wavelength? How much wavelength of light energy should pass during the experiment? Again, that is again trial and error. We'll pass a different wavelength of light, the one which absorbing a maximum light energy, and that light energy or the wavelength we normally choose. The colorimetry concerned with the determination of concentration. How? By the light absorbing substance, by the measurement of relative absorbance of light with respect to a known concentration of the same substance. That's why we'll prepare a known concentration of that particular substance. Say if you want to detect a copper cupric ion, then we have to prepare a cupric ion solution. Okay, with respect to that standard solution, we'll detect the amount of that concentration of that ion present in a given sample. See here, it depends upon the two laws, that is Lambert's law. The Lambert's law states that the decrease in intensity of the monochromatic light or the decrease in or when a monochromatic light is passed through a transparent absorbing medium, the decreasing intensity of the monochromatic light with respect to the the thickness of the medium, okay, is directly proportional to the intensity of the light absorbed by the substance. We simply write it as a it is taken as minus the decrease in intensity of the light, okay, I naught by d thickness, or you can take it as Ig transmitted is directly proportional to C. Instead of writing this, we may express this one by exponential term like Ig is equal to I naught e to the power minus KL. That is, when a monochromatic light passes through a transparent light absorbing medium. So I'll take a medium like any solutions. Say I'll take the Cu2 solution which contains Cu2 plus, and I'll pass a light. Okay, this should be a transparent medium or a transparent one. That means the total transmission or the light should transmit it, okay, through this medium. The intensity of the transmitted light usually decreases exponentially as the thickness of the medium increases arithmetically. Here the thickness is very less. I can take another cuvette tube with a little larger thickness. Okay, I'll take same concentrated solution. Again I'll pass. What is the amount of light transmitted is equal to, it depends upon the thickness of the medium. As the thickness increases, the light absorption decreases, or in other words, the transmission decreases. And that itself what we called it as a Lambert's law. That is, when a monochromatic light is or passed through a transparent light absorbing medium, the intensity of the transmitted light, the intensity of this transmitted light decreases exponentially. It decreases exponentially, okay? It decreases exponentially as the thickness of the absorbing medium increases arithmetically. So as the thickness increases, like 1, 2, 3, 4 thickness, so their absorption, transmitted light, decreases exponentially. Okay, so that law, what we called it as a Lambert's law, it depends upon the thickness of the medium. Okay, the Lambert's law depends on the thickness of the medium. When a monochromatic light passes through a transparent light absorbing medium, the intensity of the transmitted light decreases exponentially as the thickness of the absorbing medium increases arithmetically. Mathematically, we will write Ig is equal to I naught e to the power minus KL, or we can write Ig by I naught is equal to 1 by, it's actually 1 by e to the power, it's actually plus KL, e to the power KL. What is this IT by I naught? IT is the intensity of the transmitted light. I naught is the intensity of the incident light. And the K is the absorption coefficient and L is the thickness. Here the ratio IT by I naught, the transmitted light by the intensity of the incident light, is called transmittance, called it as transmittance. And the reciprocal of the logarithmic of the transmittance is the absorbance. That is T is equal to IT by I naught. Transmittance T is equal to IT by I naught. Then what is absorption? It is the absorption A is log of 1 by T, or we can write it as the log of I naught by IT. So absorbance of a solution is directly proportional to the logarithmic of intensity of the incident light to that of the transmitted light. Okay. In the case of Beer's law, it relates with the concentration of the medium. Beer's law relates with the concentration. The same way we'll express when a monochromatic light passes through a transparent light absorbing medium of a constant thickness. Here the thickness we kept constant. The intensities of the transmitted light decreases exponentially as the concentration of the light absorbing substance increases arithmetically. We'll take a same this one thickness tube. In this tube we'll introduce a solution with the varying degree of concentration. It's not same. As a concentration like 1, 2, 3, 4, like 0.1, 0.2, 0.3 normal concentration if you take, then if you pass a light, okay, a light passes through a transparent light absorbing medium of a constant thickness, the intensity of this transmitted light decreases exponentially as the concentration of the medium increases arithmetically. We may express IT is equal to I naught e to the power minus K1C, where C is the concentration of the solution. K1 is a constant. And we'll combine the 1 and 2 equations. First equation, it relates like this. IT is equal to I naught e to the power minus KL. This one is IT is equal to I naught e to the power minus KC. Okay, or K1 KC. That means the some terms are same. Then we can write it as IT is equal to, we may write this one, IT is equal to I naught e to the power minus KCL. Yeah. Or in the place of K, we can write it as epsilon, called it as molar absorptivity, or in other words, molar extension coefficient. Okay. See, the complete term is a constant, so that the absorption, this IT by I naught, we can write it as IT by I naught is equal to epsilon CL. Okay. And this is actually the log IT, E term is there, that's why you'll take it as a log IT by I naught is equal to epsilon CL. So, what is that log IT by I naught? That is absorption is equal to epsilon CL, or we can write absorption is directly proportional to concentration and the thickness of the medium. Here, if you kept thickness constant, then absorption of a solution or absorption by the solution is directly proportional to the concentration. The collectively what we called it as Lambertz-Beer's law. Okay, that is Lambertz-Beer's law is mathematical expression is this one. Log I naught by IT is equal to epsilon CL or A is equal to epsilon CL, where A is the absorption. Epsilon is molar absorption coefficient, C is a concentration, and L is the thickness of the medium. This is like, or we can write it as absorption is equal to epsilon CL log I, because log I naught by IT is equal to absorption, that is log absorption is nothing but in reciprocal of logarithmic of the transmittance or minus log T. If the path length of the cell is kept constant. What is that path length? Path length is nothing but the thickness of the medium. If you keep this one constant, this is already constant, then absorption is directly proportional to concentration. Absorption is proportional to the concentration C. A is equal to constant. So how we express the Lambertz-Weiss law? The Lambertz-Weiss law we normally express it as A is equal to epsilon CL. Okay, or you can write it as log I naught by IT is equal to epsilon CL. When a monochromatic light passes through a transparent light absorbing medium, the intensity of the transmitted light decreases exponentially as the thickness of the medium and the concentration of the light absorbing substance increases arithmetically. If these two are increases arithmetically, at the same time the transmitted light decreases exponentially, then that law called it as Beers-Lambert's law. When a monochromatic light passes through a transparent light absorbing medium, the intensity of the monochromatic light or the intensity of the transmitted light decreases exponentially as the thickness of the medium, that is Cl, and the concentration of the absorbing substance, light absorbing substance, increases arithmetically. And this is what we call it as a Lambert's-Weiss law. Mathematically, we may express log I naught by Ig is equal to epsilon C. See, this is a theory behind the colorimetric estimation of a substance which can able to show a color. Observe the instrument. There you can observe only the outer structure. You are making some something like 2-0 set. Okay, calibration of the instrument, one thing. Only that one you observed, and you are introducing some the tube. Okay, that is what we call as a Couette tube. So in that Couette tube we will take the solution, and that is introduced to our sample cell, it is called. It is introduced to the instrument, and that light, it absorbs some amount of the solution which present in the things, absorbs some light energy and will get some reading. Okay, but in that, what are the essential parts present in the instrument? The essential part of photoelectric colorimeter are, the first thing is light source. Okay, light source that absorbs light energy, or they produce light energy, and that light energy is absorbed by the colored solution. And here usually we'll take a LED source, tungsten bulb, but while introducing the light energy, here we'll take a light, and then that light is passed through a lens in order to just to make a narrow beam. So complete this light energy should fall on the test solution. For that purpose, we make it to we use some lens to make a parallel beam. Then, is we send the entire, the complete the monochromatic light, or we restrict. Usually, a filter is used. It's a device which is used to produce a monochromatic light, and very important thing is with the desired wavelength. Monochromatic light with desired wavelength. Monochromatic light with desired wavelength range is chosen, where the solution gives maximum absorbance. That is very important. It should absorb a maximum. Say if you use a component like Cu2+, it will absorb a maximum light energy at 620 nanometer. And if you use an iron-like component at 420 or 480 nanometer, it absorbs. The reason here cupric ion produces blue color, whereas this produces red color. So maximum absorption is observed at 480 nanometer. It depends upon the color developed by the solution. Whereas in copper, the maximum absorption is observed at 620. So that means a filter is used to restrict a monochromatic light of desired wavelength. Okay, see it, and that wavelength, in that wavelength, the metal ion which is present in the test solution should absorb maximum light energy. Then next comes to a sample cell. Usually the sample cell is also called as a Couette tube. See, this also called as a Couette tube. Okay, it is also called as a Couette tube, where the sample is taken. This Couette tube is usually made up of, a glass tube just to absorb light energy or just to hold a solution. We'll use sample and their thickness is the same because during the experiments we keep L constant. So that's why we use the same thickness of cuvette tube throughout the experiment. Then a photocell, it absorbs some amount of light energy and that converts the emitted light energy, okay, or in other words, absorbs the light energy into an electrical signal, and that is fall on the photocell, and finally it is displayed in the digital display. Okay, these are the instrument setup: the LED source, lens system, optical fiber, test solution, photocell, and the display. Okay, next thing. What is the application of colorimetry? See, the colorimetry find application when the solution can able to show a color. A colored solution concentration can easily be predicted on the basis of Lambert's Bayes law or using colorimeter. The one main application is the detection of cupric ion concentration, okay, in the solution using colorimeter. Or we can give a brass solution. The brass solution contains some amount of cupric ion. We are not known how much quantity of cupric ion present in that brass sample. You can by titration also you can able to find the brass solution concentration or a cupric ion concentration in brass solution. Or even by colorimetry, we can able to find the cupric ion concentration. That's why the brass solution containing cupric ion usually treated with the ammonia. You already know the brass solution is a copper tint in color. That is a very low light blue color, bluish green color exists. The absorption of light energy by this complex is very less. Compound is very less. To enhance the absorption rate, we'll introduce ammonia solution. So as a result, it produces a soluble complex called cupromonium sulfate, okay, with the characteristic deep blue in color. And this is applied only to a very dilute solution, okay. To detect the concentration of cupric ion in the brass sample, particularly a dilute solution of brass is used. Here, cupric ion is made to react with the ammonia, forming a deep blue colored cupromonium ion. And by detecting the concentration of cupromonium ion formed or the light absorbed by this cupromonium ion, we can able to find the quantity of copper present in the sample. So the absorption of this solution is measured at 620 nanometer. This is a lambda max since the complex shows maximum absorption at this wavelength. Even practically, we may not use 620, even 580 is sufficient. 580 to 620 nanometer is used. Then what we done? We prepare a series because it is a comparing the concentration is determined by comparing. So here it is a relative absorption of light with respect to a known concentration of the same substance. So that's why we'll prepare a known concentration of the substance. That is, a series of standard solutions are prepared by using brass solution in different 50 ml standard flask. Okay. So how we conduct the experiment? We'll prepare a stock solution of brass. Then that from the stock solution, we'll transfer a solution like 2, 4, 6, 8, 10 ml of brass solution into a 50 ml standard flask. Okay, we will take around 6 to 7 50 ml standard flask. Okay, in each standard flask, we'll introduce this. This is not RB flask. I'll take it as a standard flask. We'll introduce 2 ml, 4 ml, 6 ml, like 8 ml, like and 10 ml of Cu2 plus ion solution is introduced first. Then to make it to a cupromonium sulfate, to each standard flask, 5 ml ammonium hydroxide is introduced. To each standard flask, 5 ml ammonium hydroxide is introduced. And we'll take one test solution, okay, some X quantity of test solution. is taken. To this test solution also will introduce 5 ml ammonia. And one more will take a blank solution to standardize the instrument. To that also will introduce 5 ml ammonia. Okay. The same volume of ammonium hydroxide is introduced to the test solution. Okay, as well as to a blank solution. Then all the solutions are diluted up to mark and shaken well for uniform concentration. That means we are preparing a different standard solution with a varying degree of brass solution, 2, 4, 6, 8, 10 brass solution. Then a blank solution is prepared by taking 5 ml ammonium hydroxide in 50 ml standard flask, dilute with the distilled water and make up to mark and shake well for uniform concentration. Then we'll measure the absorbance of each of the stock solution with reference to the blank solution at 620 nanometer. We'll take first 2 ml of the solution which contain 2 ml of brass solution in the cuvette tube, and you know the instrumental setup. Okay, in the cuvette tube we'll take 2 ml. You consider this is a colorimeter. Here you can observe one set. Okay, display. Here there are two knobs. One is a wavelength knob, another or the filter knob is present. Okay, then some hole in that will introduce a cuvette tube. Here first we'll press the set and make it to 0 reading. Then okay, we'll introduce a lowest concentrated solution, say the solution which contains 2 ml. Then we'll observe the absorbance of that reading. Say the absorbance of that particular may be for, I'll take for 2 ml, it may be, we may observe 0.9 or 0.09. Okay. Then we'll introduce the solution which contains 4 ml, maybe 0.18, 6 ml, 0.26, like we'll measure the absorbance of each solution against black. Again, each time we'll standardize the instrument and we set up the wavelength at 620 nanometer. Then we'll get a different series of standard solution absorbance. We'll take a volume of Cu2 plus used and the absorbance along y-axis. See, and then we'll plot the graph. So we'll put the points for 2, 4, 6, 8. We'll get the straight line passing through the origin. And this graph, what we called it as calibration curve. Okay. We'll plot the calibration curve by taking absorbance along y-axis and the concentration along x-axis. We'll get a straight line passing through the origin. Why it is passing through the origin? That is according to Lambertz law. It is according to Lambertz law. We'll get. Then we already prepared a test solution. The test solution absorbance also detected, and their absorbance should be in this range. Okay. And say the absorbance is X. Corresponding to this X, we'll find the volume of Cu2 plus present in the sample. And this is applicable only to a dilute solution. In this way, we can able to find the concentration of Cu2 plus ion in a test sample. Okay, using calibration graph. And what is the advantage of this? The advantage, it is specific to one chemical species. Microscale quantity can be determined. Very dilute color solution can be estimated accurately. That is very important. It's applicable to a dilute solution. Then cost of the instrument is very high and the calibration is needed before analysis. These are the some drawbacks we observed under colorimetry. Okay.